Well, welcome everybody to GeoHug, and today is going to be such a good one. I'm thrilled that we have Mark Gabbitus joining us today. So Mark has been involved in the mining industry for over 30 years and is currently the business development executive at Ideon Technologies, where he's looking at emerging markets globally where Muon Tomography solutions can make a difference. And it is going to be brilliant as he takes us through some case studies showing where MuT has been used and the value that it has added. So this is going to be a fantastic session. I hope you all enjoy it. Please use the chat and we'll be opening up the floor at the end. But yes, thank you so much, Mark, for joining. It's awesome having you here.
Hey Jess, how are you?
Good. Excited.
I don't like it when you say that I've been in the industry for 30 years.
I
I
know.
feel exceedingly old.
You'll look it too. No.
Thanks, mate.
um, but no, I was curious what got you into geology to begin with.
Yeah, well, I had a really inspiring teacher at school. I wasn't particularly good at school. I didn't really enjoy the whole process of school, but when I did geology in my what we call what would be here at year 11, year 12 in my A levels. I had just this amazing, inspiring teacher who I couldn't think of anything I'd rather do than get into geology. Went and studied at uni, moved to Australia, and the rest is history, as I say. But yeah, I couldn't imagine doing anything else.
Wow, that is awesome. It's teachers do make such a difference. It's that's awesome that they got you into it.
Oh, yeah, and I look at it with my daughters, right? The engagement change from year to year depending on which teacher they have, whether it's
Yeah.
math or French or physics or biology. If they have a good teacher, they are super engaged and do well that year. If they have a teacher that's perhaps less engaging, you can see their marks drop off. So it is massive. Big
Yeah.
shout out to the teachers, pay them more.
Yes. And yeah, so what have been some, because you've been in industry itself, you've worked in technology, you've done all sorts of weird and wonderful things. I'm curious, some highlights for you so far.
Highlights. Look, I mean, in terms of roles, starting up the ground rush mine in the Northern Territory and getting all the mine control systems set up or mine geology system set up was probably the main career highlight from a geological perspective. But personal highlights, some of the travel I've done, going to Grasberg, being at 4,500 meters above sea level with a glacier on the equator, and hanging out with Indonesian nationals there doing training when I was at mine site was just spectacular. I'll never forget the trip I did to the far west of China to a little gold mine out there, and really just the people that you meet, right? I mean, you and I met a long time ago.
In
I
Bali, wasn't it?
Indonesia. Let's call it Indonesia. We can never say that it was a Balinese conference. It was an Indonesian conference. But yeah, it was. You were 12 or something, and
Yep, little baby I was.
yeah. But no, that's really the highlight of the career is people around the world, and those mining connections that you make, and it's really come home to me a few times over the last 12 months where I've changed jobs, moved around, and reached out to people, and they've come back to me really quickly and engaged. That's really heartwarming that people are generous with their time, and B, that obviously something I've done has made a bit of a difference to some people's lives and they've come back.
No, that's brilliant. I love that. And I'm very excited to see your pet rocks today. I'm
Oh,
curious
all
what
right.
ones
Well,
you've got for us.
so I guess three phases of my geology career, I guess. So starting out as a very young lad in North Yorkshire, we've got excellent fossil beds, Jurassic fossil beds along the coast there. Ammonites. I've never found a plesiosaur or an ichthyosaur there. I have seen their footprints, but finding ammonites was really the thing that got me into geology and earth sciences as a youngster. Then I went and came to Australia and went and worked in Meekatharra, spent 4 years in Meekatharra. And when you say that to Australian people, they kind of take a deep intake of breath. It's like, wow, why would you spend 4 years in Meekatharra? But I loved it. It was probably the best 4 years of my life. And one of the minerals that we had there is a ultramafic alteration mineral, the green mineral. It's a bit hard to see with the light, but it's got the it's got the amusing name of being called fuchsite. So that's why it's my favorite rock. And then moving up into the Northern Territory, one day I was in the pit and I noticed a little glint in the ground, and there was a gold vein running through a waste area. So me and my buddy on a Sunday took the pickaxe and the shovels down, and we actually dug all of this gold vein out. It was in a waste area, like I say, it was only a narrow vein. And some of this gold now lives in Newmont's head office in their reception, and they show this all the time. And when I left, they gave me this piece as a reminder. It's actually comes on a mount and everything. I've even got the piece of paper saying I'm allowed to have it. So that's pretty rare that you get that opportunity to take a piece of gold away from a mine. So I'm pretty proud of that. So they're my free pet rocks for today.
I love that. Thanks for sharing, Mark. And thank you again for being here. I'm very excited to hear, what you've been busy working on. So if you want to share your screen and we'll get stuck into it. So,
I've recently started working for a Canadian technology firm called Ideon. And, I've, like you said prior, I moved out of geology into technology. I've always been really passionate about the technology we use in mining, both from a geological perspective, but also from an engineering perspective. I think that the application of technology is really important, and especially when it can help change some of the mindsets, bring things forward, do things better, do things smarter. That's what I'm all about, and that's what I've always been about. So Ideon attracted me because they're essentially applying Muon Tomography to the mining industry. And we'll talk a little bit about Muon Tomography later and what it is, but I thought you've bugged me for a few years now, Jess, to do a Geology 101 type session. So I thought I'll take that to heart and I'll do something along those lines. So it won't take long, but maybe people can bear with me. So I thought we'd start by taking a really quick journey through space and time, if that's all right with you, Jess.
Oh, it sounds good, but we don't have all day, so don't do your normal thing and bore us with all the details.
Well, that's really harsh. And I'm offended, but okay, I'll try and keep the story of how the universe and everything created it was short and sweet.
Okay, go on then.
All right, so disclaimer here, I'm going to be slightly controversial, and I won't be following the Usher chronology that tells us the universe was and everything in it was formed on October the 23rd, 4004 BC. I'm going to be running with the boring old standard model of cosmology, which states that as far as we know, in the beginning, there was nothing, no space, no time, no energy, and no matter. And then one moment, 13.8 billion years ago, that all changed. And the Big Bang happened. It is still happening, maybe, i.e. multiverses. And as the universe expanded and cooled, hydrogen and helium atoms were formed and a little bit of lithium. So there's not a lot to get super excited about here. I guess lithium, we mine that, but without the nickel, cobalt, copper, graphite, we're not getting batteries. So, let's see what happens. After about 100 to 200 million years, stars started to form, clump together in galaxies, such as the Milky Way. Now, 100 to 200 million years sounds like a long time to people. Jess, do you have any idea what the difference between, a million, 1,000, a billion is?
It's not really.
Big numbers.
Yeah, big numbers.
That's what it is. So, in context, 1,000 seconds is about 17 minutes, okay? Which is a quick walk to the shops. 1 million seconds is 11 days, which is, like a good holiday. 100 million seconds is 3 years, so a uni degree. But 1 billion seconds is 32 years. So that's the difference between going from thousands to millions to billions. It's not just a big number, it's a big number. And geologists love this stuff, right? Or I do anyway. So we get stars forming, and we have different types of stars. So we have small stars like the sun, and they can fuse elements up to about oxygen in the periodic table. Anything here that interests you, Jess?
Oh, I like carbon, hydrogen, and oxygen.
And that's because they're the essential building blocks of alcohol, correct?
Moving on.
Right, okay. And then we have massive stars. So massive stars can fuse elements up to iron. And if that was the end of the story, the universe would be slightly different and boring. Although, I like my vanadium strengthened tools, but I don't get that excited about them. So we need something else. And that something else is what we call a supernova. So when a large star runs out of material to fuse, essentially it runs out of energy, and the pressure of radiation going outwards can no longer hold the force of gravity. So it collapses in on itself and then explodes in what we call a supernova. Oh, and that's where, pretty much all of the heavier elements like gold and copper are produced. Anything in here that interests you, Jess, perhaps?
Well, I've got really simple tastes, so I'm thinking gold, platinum, and carbon in the form of diamonds.
Excellent. Yes, I figured that would be your interest area here, Jess. Some of the elements don't get created in supernovas. They actually get created by humans or in very small quantities. So some of the radioactive elements actually get created elsewhere, but pretty much everything that we care about is created in supernovas. So those supernovas essentially blow up. You get this big cloud of dust and a collapsed core. And the shock waves from these supernovas compress these dust clouds into nebula, where gravity can take effect. And essentially the star building process restarts. And importantly, the solar system building process. So 4.54 billion years ago, when the Earth was formed, its elements essentially came from supernova. So we are literally made of stardust. So you can take that one to the bank, Jess. You can keep that one for a chat up line or whatever you need later on. Okay, so why am I talking about supernovas? Well, supernovas do all this amazing stuff and create the elements that we're interested in, but they also create cosmic rays. And cosmic rays, they're high energy protons, helium nuclei, traveling at nearly the speed of light, and they're constantly raining down on the Earth, all the planets, but on the Earth is the only bit we care about at the moment. And when those cosmic rays interact with atoms in the Earth's atmosphere, for example, nitrogen or oxygen, they create a shower of secondary particles called, create a shower of particles called pions and other stuff. And those pions are short-lived and decay into muons. Muons are traveling close to the speed of light, relativistic speeds. They only live for about 2.2 microseconds, but because of that speed, they're hitting the Earth and traveling through the Earth. And they're weakly interacting, so they actually do penetrate quite deep. And it's these muons that we are harvesting at Ideon to help in exploration for minerals and to observe mining processes as well. So essentially, we're using the cosmic rays produced by supernova to find the elements that were created by supernova. So it's like we've come full circle. So that's why I bored you a little bit at the start. So I apologize for that, Jess. Oh, wow. All right. Hopefully the geos and the scientists on the call were in agreement with me. And there are questions at the end. So if anyone wants to question my story about the galaxy's, the universe's evolution, happy to do it. All right. Shall I carry on, Jess?
Yes, please do.
Okay. Wow. All right. So we're going to skip forward about 4 billion years here to the late Ordovician, early Silurian, and we're going to go over to central New South Wales. And we're going to go and have a look at how we've been helping Northparkes there with some of their safety and productivity challenges. And then we're going to do a 100 million year jump to the late Devonian and go into the Yukon in Canada. And we'll take a look at how we've been helping Fireweed Metals identify new drilling targets at their Mac Pass project. Is that good for you, Jess?
This sounds awesome. Go for it.
Brilliant. All right. Okay, so Northparkes. Evolution Mining have been mining at Northparkes for a long time, and they've been block caving there since 1997. So it's actually the first operation in Australia to run a block cave. And they came to us last year to help them with some monitoring, with a monitoring solution. So if you don't know Northparkes, it's in New South Wales. It's near Parkes, which is the site of The Dish. So if you're Australian, you've definitely seen the movie called The Dish. If you're not Australian and you haven't seen the movie called The Dish, go and get it out. It's one of the best movies ever made. Then watch The Castle, but we'll talk about that later. But definitely watch The Dish. It's a big porphyry-hosted copper gold deposit, and also worth going to Parkes because they have an annual Elvis festival, surprisingly. So block caving, I know this is a geo forum, but we do have to mine this stuff eventually. So block caving is one of those mining methods that we use to get these deposits out, and it's a pretty complex mining method, and it's really hard to monitor. Essentially, once the cave starts propagating, it's really hard to see inside of the cave. We put sensors down there. Sometimes we try and drill holes into the cave to see if there's an air gap or what's happening in the muck pile. But essentially, it's really hard to monitor. Muon Tomography measures density. Essentially, it's a measurement of density, and which is really important because with that, we can see areas of high density, we can see areas of low density, and an air gap, which is a critical safety challenge in a block cave, is a low density area. So we can observe that at relatively high resolution. So why is that? So when we engaged with Northparkes, they asked us, they're going to start a new lift. Can we help them increase their safety margin by observing and informing them about the size of that air gap? Sorry, should probably just say why that's important. So if you have a big air gap above your muck pile in the caving process, i.e. you're drawing from the bottom and it's not caving properly and you get an air gap, if you get a big rock fall, especially when you're quite early in the mine, essentially you're compressing that air down. It rushes through the muck pile, comes out the draw point, and essentially creates a gale down your development drives, and it can be dangerous to even life-threatening, and it has been in the past. So knowing the size of that air gap and therefore being able to control, or at least monitor it and control some of the controllables is really important. We can do that. Achieving greater operational predictability. If anyone's ever worked in a block cave or looked at block caving, it's really hard to know what's going on in the muck pile. Essentially, you're just constantly drawing and hoping that the grade is coming out how you expect it to, in the right place, and that the cave is progressing in the right direction. By being able to monitor the shape of that cave and how materials progressing through that cave, that means that you can then go and do that third point, which is proactively manage that and control the draw. So we put our sensors in. So we have this is our panel type sensor. We installed them underneath the block cave and the draw point area, and we did that in February 21st of this year. And 60 days later, we were producing cave images. So it was a safe implementation, and yeah, it only took us 60 days to get the first set of data. And we're now producing monthly cave models for them. So what does it look like? If anyone's super interested in this, we did a webinar with Northparkes 2 weeks ago, and that video is available. You can go and see all of the results. But what are you seeing there? That gray, I'll keep playing that on loop for a while. That gray shape is a historical cave, the original cave that they mined, and then the green wireframe is a new lift that they asked us to monitor. And so there are a couple of challenges with this. One, we want to know how that cave is progressing upwards. We want to know the air gap inside of it. And we also want to know how it's interacting with the existing cave. So if you kind of think about a cave, think about an upturned bottle full of sand. You take the bottom out and the sand pours out. You're not really left with an empty bottle. In this case, material from the surface, waste material, collapses in and fills up that cave, but you don't want that material. That's waste. When we do this second lift, there's a potential that some of that material will move into the new cave, and that's a challenge. So that's one of the things that they wanted to monitor. If we move to another view. So first of all, sorry, I should be really clear. This wireframe here, caves around the world have never had this definition of their cave shape. There's no way for them to get that without muon tomography. The best thing they can do to date, the state of the art to date, is to try and drill some holes into the cave and find where that contact is. So you might get a few pierce points, but you don't get that level of resolution and detail. So this is a first, world first, really important. That's good. But what we also are able to do is measure the density of the material inside of the muck pile. So these aren't just homogeneous chunks of earth. That's not how the world works. There are high density areas, there are low density areas. And, sometimes there are situations, and very commonly, where high density areas equate to grade and low density areas equate to waste, for example. And if we just skip over to this slide deck, I think my animation works. Yeah. So these are 3 time period slices through that muck pile. And so that's April to May, May to June, June to July. So you can see how the cave is growing. The blue area is the air gaps. This light blue area is really interesting. This is a low density blob inside of their muck pile. You can actually track it. Unfortunately, we didn't have scans earlier, but the feeling is that this is the old cave over here. This blob has actually come through from that, from the waste, the clay material essentially, that's come through from that old cave, progressed through the muck pile, and has actually come out of the draw points now. And they were they're doing sampling of that now to confirm that. But this ability to see the heterogeneity of the density in the muck pile to be able to give early indication of the formation of chimneys and pillars. So that might be a chimney forming, i.e., it's not caving evenly. This high density area here, possibly a pillar that hasn't broken and it's caving on either side of it. These are things that are really important for them to understand. They don't have virtually no ability to get that type of data today. And what they can then do is control how much material they draw from these draw points below to actually impact the caving process and control how the cave progresses. So this is actually a really, really important data set, and we're getting a lot of interest from caving operations around the world. Not that there's there aren't 400 caves around the world, but there's enough that it's generating a lot of interest, and we have implementations at a number of caves now. Jess, do we stop for questions, or do we go to the end and do questions at the end?
I think keep going and then we'll just open it up later. Yeah.
Okay, cool. Happy to take any questions on this later, guys. All right. Let's move over to Fireweed. So we're shifting our focus from, I guess, a geotechnical monitoring application to a exploration resource extension application. And we're moving from New South Wales to the Yukon, slightly different environments there. So up in the Selwyn Basin in the Yukon, it's probably one of the most prolific zinc districts. If you're aware of it, there's been lots of historical mining for lead, zinc, silver, tungsten. There's even some gold up there. And Fireweed are in this area in a place called Mac Pass, looking for gorillas, sediment-hosted stratiform, lead, zinc, silver type mineralization. And why Muon tomography is a really good solution for that type of mineralization that we have a very dense mineralized material in the, obviously lead and zinc, pretty dense minerals, but or elements, but the minerals that they're associated with are very dense. And we have a low density shale background. So we get a really good contrast. So high density areas stand out pretty well. If anyone's ever been to the Yukon, I haven't, but it gets pretty cold in winter, I hear, and they can't do a lot of drilling there. So Muon tomography surveys can take anywhere from 2 or 3 months up to 6 months, depending on depth and depending on type of material. So what we did was Fireweed drilled some holes for us prior to the winter season. We installed our borehole detectors this time. So we have our panel detectors that we put underground, and we have borehole detectors that can go down a hole. We installed our borehole detectors into there, and the problem statement that came from was running a survey over the winter to search for resource extensions, satellize mineralized models, provide a 3D model of their mineralization, i.e. their density is essentially what we're creating, a density model, and using that to validate some of their current geological hypotheses. And really the key statement there was, can we accelerate discovery time by surveying large volumes of ground quickly and reduce the number of dry holes that they have to drill, i.e. can we maximize their drilling budget? So we implemented and installed our borehole detectors just prior to the winter season. Again, successful implementation, very safe, worked really well with the Fireweed team. And these borehole detectors lived in the ground over the winter for 5 months, under snow, minus 40 degrees, live communication and power maintained for greater than 90%, i.e. sometimes we had to go out and refill the generator with diesel and restart it. But that was pretty much, I think that was once we had to do that through the whole winter. And we were essentially harvesting muons for that period of time. Now, whilst the project went on for 5 months, we were surveying for 5 months. We were providing data before that, but we just did a full 5-month survey. So the green and red slice through, that is the resultant model that we created for them. The red wireframes that we'll be slicing through are their geological models, and then these are the 3 drill holes that we used for the survey, and the orange circles are the different borehole detectors that we put down. So we actually chained a number of borehole detectors down the hole to give us better coverage. And really good alignment with their geological modeling and their grade drilling on ore to density, i.e. there's a really good correlation between grade and density. So that gave them a lot of confidence in the technology, because it's really nice first time you use this to run it in areas where you've got other data sets. And it's given them a lot of confidence moving forward to run further surveys where they have no drilling or very little drilling. This was also a place where we took some of the existing geophysics data. So we took their gravity. They had a really good surface gravity data set, and we actually did a joint inversion of the gravity and Muon tomography to get actually better results. And sorry, you actually do see slightly better results when you bring the two together, especially at really near surface contacts. But the big thing that we discovered there was that we found new exploration targets that they didn't know were there. So they weren't identified, or they don't show up from their gravity survey. Muon tomography identified them. So we found new shallow targets. We found a really deep one to the north side. It's actually not on this slice, but it's just over here that they're drilling right now. And so they've gone away and started doing their drilling program, their 2025 drilling program, to go and test these targets. And hopefully we'll get some results from Fireweed pretty soon. And that was done from 3 drill holes, 21 detectors, sat there over the winter when nothing could happen, probably doing the work of approximately 50 drill holes. So, that just gives you an indication of what we can do with this technology. So I thought I'd end up with a closing discussion about what the value of Muon tomography is. And rather than me telling you what I think the value of it is, I thought I'd pose 3 questions to the group. And the first one is, what do people think about the way we measure density today? There are 2 primary methods. We either take some core or a piece of rock and we weigh it in water, and we weigh it in air, and the Archimedes principle, or we use a downhole gamma probe, active source. Do we believe, people on the call, do we believe that density is an important component of the ore body knowledge story? I've been spending quite a bit of time looking at mineral resource statements over the last few months, and it's quite scary how few samples are taken to measure density compared to grade, even structural data. And yet, if you kind of think about it, you need density and you need grade to calculate metal. You need density and volume to calculate your tons. So it's essentially half of the story for a lot of the critical results that we have to create in our MRE, and yet we're doing it off very poor data sets. Now, that's not to say, I'm pretty confident that most geos on the call would agree that it is important, and they also understand why they can't collect. I understand why collection of this data is difficult, But let's have a conversation around that. And then, I'd be really interested to hear people's opinion on what they think the real value of muon tomography is for them. So I'm going to stop talking because Jess tells me I'm boring, and open it up for the for the floor. And I'd be really happy to take questions, comments, feedback, whatever.
You've blown me away, Mark, because that was actually super interesting. So thank you.